Okay, I will start with noise today then. So far we have, if I briefly recap whatever we have been doing for the last 8 lectures was give you a very top level overview of the entire RF chain. And sometimes we went into some amount of detail as to what are the some of the nuances that govern our decision making as to which type of architectures we need to use. And also, we also saw what the interplay between multiple stages in an RF chain. For example, you cannot simply choose any mixer topology, or you cannot simply size the transistors of a mixer in any random fashion if you do not take into account the swings at the output of the LNA. Similarly, we also saw certain constraints when it came to deciding on whether you need to have a matching or not, right? At the interface of the LNA and the basically at the chip boundary, at the interfaces of the chip boundary. So we spent a considerable amount of time on motivating the architectures. We also saw one lecture we also devoted to how to manufacture clocks. One lecture we devoted to what are the efficiency matrices of power amplifier. Then also we talked about what are the basic requirements, what are the basic differences between a receiver and a transmitter architecture, even though they kind of look like the dual of each other. And one guy transmits, up converts and transmits, other guy down converts and receives. But the requirement from a designing perspective is not same. So those are the things that we motivated and looked into. In the previous lecture, we talked about 2 receiver architectures which are commonly used in the literature. One is 0 IF receiver or 0 DC receiver or a homodyne receiver. The other one is non-zero IF or super heterodyne receiver. So we also talked about some of the benefits. One of the benefits of, obviously the 0 IF receiver has a benefit that it is much simpler its architecture is very simple, right? You just have an LNA, you have a mixer which down converts and a low pass filter and you are done. But then we saw there are issues with that. And the issues was basically because you have leakage through the capacitors of the mixer switches, which in effect comes back as input into the mixer switches and causes all sorts of distortion issues further down the signal chain. Also, the additional problem is it also goes through to the antenna at a fairly high power with respect to whatever you are receiving, and it can cause problems to the neighboring receivers. Right. So that was the big problem of 0 IF receivers. So then we hypothesized that how can we figure it out? How can we solve this problem? One of the ways we could solve this problem is to ensure that we do not keep your IF do not keep the center frequency of reception to the same as the filter frequency, right? So or the LO frequency. So the local oscillator frequency we moved away from the reception frequency. So that helped in reducing the out of band emission. That also helped in ensuring that whatever is coming through, right? Whatever is coming through as an input does not fall into the range of inputs that is of interest to us, right? So if I go back to this architecture, so what we saw was if this center frequency FLO, right? If this frequency here we called it FLO plus IF, but if this frequency is not the same as the reception frequency, then whatever comes back through as a leakage, right, is not at the reception frequency, right? So if this is not at the reception frequency, then based on some sort of filtering down after mixing, I can get rid of whatever is supposed to be the unwanted LO injection, and then we can do some sort of filtering later on to bifurcate the junk that we are putting into our signal chain and distinguish it from whatever we want to receive, right? So ultimately, the whole game is you want something, you have something wanted, you have a wanted signal, you have everything that is unwanted. How can we distinguish between the wanted and the unwanted, right? So there are several ways of doing it. Filtering is one of the way of doing it. Here, fortunately, the unwanted part is something that is in our control, right? The choice of LO frequency is in our control. So we'll simply not choose it to the frequency of the input. But then the problem comes is that now you have to have another set of down conversion, because now after the first mixer, your output is not around DC, right? So the second set of down conversion was required, and then we eventually went into a low pass filter, and that did the job. The argument that could have come up was, why is the second set of down conversion not a problem, and the first set of down conversion, the second mixer down converts the input to the second mixer to DC. So that should also have the same problem as the first mixer. The reason it doesn't have is, well, it's not as high. The problem is not as big a problem in the second case, because we saw that the injection is proportional to the frequency, right? And the second set of mixer is operating at a much lower frequency than the first. So that injection, number one, that reduces the problem per se. The second thing that reduces the problem is you will probably going to have some sort of gain before the first mixer, which means the signal would have been amplified before it comes to the second mixer, right? So it is not sufficient to say that I will reject any unwanted stuff. You will never be able to reject completely any of the unwanted stuff. So you'll have to make a call between how much you want to reject with respect to something, and what is with respect to the wanted signal. So if the wanted signal is very high, then you can get away with some amount of unwanted stuff, right? So since the second mixer comes after further down the signal chain, and you probably have some sort of amplification, maybe a LNA or something, or maybe even after the first set of mixers, the first set of down conversion, you can have a amplifier. So that way the problem of direct injection is mitigated, right? So get away with doing direct zero DC at the second set of mixers. Okay, fine. So that was the overall motivation of whatever we have done till now. The difference between zero DC and super heterodyne we talked about in the last class. Any questions about this? Okay, fine. So if there are no questions, we can proceed to today's lecture. So I have alluded to noise in various ways at multiple times to the course in a very hand-wavy manner. What I'll do today is try to formalize it in a certain way, and then you'll see that how it affects the overall performance of the RF chain. Okay. So now, folks who have not taken 613 till now can comment. What is your understanding of noise? If I say noise, what do I mean? Okay, thermal noise. Anybody else? I know you know it because you're working on ADCs. Many atoms wiggle, that is true. Basically, many atoms wiggle in a random motion. So fine, that is one, that is a source of noise. One might say that is a source of noise, but even without going into the causality of noise, right? Why noise appears? How does noise manifest in signal chain? Right? Have you seen any evidence of it if we have done experiments in the lab and all? You have desired signal, you have unwanted signal. Noise is unwanted signal, right? So an unwanted signal can be many things, right? For example, so far we have talked about one example of unwanted signal arising from somebody else talking in the next channel, right? So can we say that is a noise? That is unwanted for sure. Can we say that is a noise? It should be random, as in when I say random, what I am essentially saying is so let me distinguish it from the example that I just gave. Whatever we are talking about when somebody is talking in the next channel, then that essentially we call it as an interference, right? Because it is deterministic. So this deterministic or random is the major distinguishing feature of, at least in electronic systems, what we call a noise and what we call an interference. Now, when you say deterministic, what do I mean? So at least if I concentrate the definition within the realms of electronic signals, if you have a sinusoid, which you probably don't want because it is coming from somewhere else, even if it's unwanted, you can figure out what will be its amplitude, what will be its phase, if you know the source, right? If you know the source, if the source is unknown, that's a different thing. But if you know the source, you know for very well what is the amplitude, what is the frequency, what is the phase, right? So that is something maybe you don't want, but that doesn't make it a noise. That's an interferer. A noise is something that even if you know that something is going to come in this channel at this frequency, but you will not be able to say whether it will be at this amplitude or this phase or something. And other way of saying the same thing is that, so let's say you take a signal, you go to you take any signal generator, right? Go to the lab, take any signal generator, turn it on. You are going to, let's say you turn it on and say, give me a sinusoid of certain frequency. It is going to give you a sinusoid of certain frequency. And let's say I'm going to observe only the maxima. I'm going to observe only the maxima of this signal. Okay. So wherever is the maxima, I set my window of observation in that span. And I keep observing that part, right? This small window. I keep observing this small window. If I keep observing this small window, I will always get the maxima. I'm not going to get a minima there, right? So this is deterministic. Okay. But if you observe this also, you are going to see there will be wiggles around this. There will be some wiggles everywhere. So it's never very clean plot, right? The cleanliness depends on the settings, but it will never be a pristine line. There will always be some wiggling around that line. So the amplitude of that wiggling and the frequency of that wiggling, you will never be able to predict. You do that now, do that experiment now, do that experiment 5 times, 10 times, 100 times, do it 1 year after, do it 10 years after. Whatever you do is you will not be able to predict the wiggling of the amplitude. So the sinusoid is deterministic, but that wiggling is not in your control. That is random, right? So that is a key difference between what we, in electronic systems at least, what we call interference and what we call noise. Okay. So the traditional way of introducing noise is essentially with an example of a resistor. So let's say I take a resistance of value R, any value R you choose. Yes.
So generally at wiggling will follow a fixed probability distribution, or will it vary?
Yeah. So now if we get into will it have a fixed probability distribution? Yes, it can have. So basically anything that you cannot characterize with respect to time, but maybe has a distribution, right? You observe it now, you observe it 1 second from now, 1 year from now, you collect a set of data points. Then obviously you can say that there is some correlation, there is some variance, there is some mean, right? So, and if you say that it is, the mean doesn't change with respect to time, the variance doesn't change with respect to time, you define it something and say that, okay, I'll may be able to associate some metric with it, right? So it is equivalent to saying that you want to, let's say, monitor traffic, right? Outside, you'll never be able to say at what point of time, how many vehicles are going to cross a cross section, right? So that's totally random. But if you have observed it for sufficiently now, long number, I mean, maybe a month, maybe a year or so, you'll be able to get a sense of at what time you have more traffic, at what time you have less traffic, right? So that way you will be able to get a idea of what is the distribution of the traffic throughout the day, right? Even though you'll not be able to predict that, okay, now I'm going to get this much amount of vehicles crossing any junction, right? So with noise also, it is kind of similar, right? So when you have a bunch of data and you'll never be able to predict exactly what you do statistics, right? So that's what we do with noise also, right? So, and we just hope that the statistics doesn't change with time, right? So as it turns out, fortunately, in case of these type of noises, it doesn't. So we should be able to we should be able to do something about it. It's all about prediction. If you cannot predict in time domain, predict in some other domain, right? So, okay. So now, so if I take any resistor, nothing connected anywhere, right? Floating, I connect it to a voltmeter. So what would I observe at the voltmeter output? Ideally, what should I observe? 0, right? I should be observed. With respect to time, I should observe 0. But in reality, this you can do experiment in a lab also. You will never get 0, you'll get some wiggling, right? Something like this. Okay. So this wiggling is, as Vasudev pointed out, it can be because of many things. It can be because the electrons they have Brownian motion, decided to cross a barrier now, and you suddenly caught it off crossing a barrier, and you register an electron crossing. So that is a one wiggle maybe, or you register 10 electrons crossing, that is a slightly higher wiggle, and so on. So you are going to see some wiggles. So that wiggle get registered in the voltmeter as currents or voltages, right? If you short it, and you observe the through an ammeter, you will get a current. If you open it and observe it through a voltmeter, you'll get a voltage, right? So you get something. Fine. So now the question is, can we do something about it? I mean, if we are getting any voltage, this looks like we're getting voltage for free, right? So can we do something about it? Can we use it to generate power? Nothing is connected here, right? By the way, why is this wiggling happening? I mean, I do not, again, let me preface the question. I'm not looking for any deep insight into why the electrons are moving in the way they are doing. I'm just asking that, is this wiggling temperature dependent? Right? So why do you say so? Right? It's kind of a Brownian motion kind of thing, right? Not Brownian motion, physicists will kill me, but essentially it is dependent on temperature, right? So if you increase the temperature, they jiggle at a much rapid speed, and you will get more wiggle. If you go to 0 Kelvin, nothing is going to wiggle and it will go to flat, right? So essentially we are getting this. If we have to extract power out of this, we are essentially saying we will be extracting power out of heat. The source of this wiggle is essentially heat, right? So we'll be able, can we extract usable power out of heat? I mean, in this sense, obviously you can make IC engines and all, right? So not talking about that. What do you think? Can we? So if we could have, then I mean, all problems would have been solved, right? So we cannot, right? So that's as some people say, it's a fact of life. You simply cannot, because if you have to, the one way to show is that I'm not showing it here, but you can show it also. If you have to extract power, you have to connect another resistor, right? Because that's what you'll be extracting power from, right? The moment you extract another resistor, and that resistor is also in the same temperature as this resistor, that is the condition. If both are at the same temperature, they are going to exchange power among each other, and thermal equilibria will obviously get established, and you are not going to get in net power out. So whatever one resistor will extract, it will also give back. So that is the reason you will not be able to get any power. The other consequence of an extrapolation of the same thing is to say that you are going to, so the mean voltage, right? So mean voltage of noise is equal to 0, right? So if mean voltage is not 0, it is equivalent to say I can extract something out of it, right? So as it turns out, the mean voltage is 0. However, the mean squared is not 0. Right? The mean squared is what? You square everything, whatever goes negative side, you flip it to the positive side. So naturally, mean squared will never be 0. It's non-zero. This mean squared voltage, in circuit parlance, obviously, what is the unit of mean squared voltage? Volt squared. Root mean squared will be volt, but mean squared is volt square. So in circuit parlance, we often refer to, when we are referring to noise, we refer to this volt squared as power. Even though power should be volt squared should be V squared by R, right? So even though it should be V squared by R, we refer to this as power in the popular nomenclature, right? So if I suddenly say that what is the noise power, don't look for another resistor, just square the voltage, okay? So this is often referred to as power. Okay. So now, as Abhay was asking, so I see that I cannot predict this with respect to time, but is there a statistical distribution to this? As it turns out, there is, and I'll just give you the definitions. If you are interested into digging deep more into it, you can look into any of the signal processing textbooks. They will have chapters and chapters on this, so we can discuss it later. So the definition is this. So if you observe this wiggling, right? You observe this wiggling now, and so basically you take this resistor, observe this over sufficiently long period of time, you are going to get some wiggling like this, right? Something you are going to get. And then you observe the mean, and you observe the mean squared voltage, right? So that you can do. So you have a data, you store the data, and you do a math operation on it, right? So you are going to get mean voltage to be 0, and you are going to register some mean squared voltage, okay? You do this operation again, maybe tomorrow, right? You are going to get a completely different waveform, which is uncorrelated to this, right? Maybe the second iteration you do, you're going to do something like this. There's no relation between the waveform on the top and the bottom, but you again do this mean and mean squared. Again, you are going to get mean to be 0, and surprisingly, the mean square that you are going to get will be exactly the same as the mean square that you got yesterday. provided you have observed it for infinitely long period of time, which is not possible, which means you are going to get close enough, right? And you keep repeating this, right? Day in and day out, you are going to get same results. So the statistics of at least the mean, when the mean and the variance of the signal doesn't change with respect to time, there is a name for it. We call it ergodic. This type of processes are called ergodic processes, right? So that apparently helps in our in making the statistics of noise, right? So how does it help? It basically says that you can do autocorrelation between this multiple these waveforms at different points of time, and then you take a Fourier transform. Do you remember what do you get if I do a autocorrelation or a Fourier transform? Path spectral density, right? So it basically says that the path spectral, if you do the autocorrelation of an ergodic process, it takes out T totally. The time goes off. Right? You're doing correlation between two signals, and if the autocorrelation, if two signals are completely uncorrelated, right? So you are going to get only one delta impulse, and then you do a Fourier transform of that, you are going to get a flat line, right? So essentially, the path spectral density of this is, by the way, thermal noise, right? This is a thermal noise. I haven't defined it, but the path spectral density of thermal noise is completely flat. Okay, so that's the good thing, because we have come from a completely indeterministic thing to looks like something deterministic in another domain, in a statistical domain, right? So that's good because it can now help us design. Okay, so I jumped few steps in the definition, so let me take it slow. So what I'm essentially saying is, if I take this resistor R, and instead of putting a voltmeter, let's say I put a band pass filter at any frequency, choose your frequency, some F naught, and I say that this is delta F, the width of the band pass filter, ideal band pass filter of width delta F, and center frequency F naught, and I observe the power here. So let's say this is power meter. Or you can assume this is a mean squared voltage meter, right? So let me just say V only. I'll say V, since we are talking about V. And I plot, and I observe the power. And I observe the power, that is, I observe mean squared voltage. Across these terminals, V1 and V2, right? So as it turns out, this is always equal to 4kTr times delta F, right? Where K is Boltzmann constant, T is absolute temperature in Kelvin, R is the value of the resistance, and delta F is the bandwidth of the band pass filter, right? So this is by observation. Okay, this is by observation of for thermal noise, right? This is we get. So what is so profound about this? This is essentially telling us that it is independent of the center frequency. It is only dependent on the bandwidth of the band pass filter, which essentially means that I keep on reducing this delta F to infinitely small bandwidth. It will still hold. It will become 4kTr times delta F, and then I can slide this delta F across, slide this F naught from 0 to infinity, right? So I can essentially decide this F naught can go from 0 to whatever infinite frequency. What should I observe? If I graph this, and let's say I graph mean squared. So let's say this is sigma. Instead of writing mean squared every time, I write sigma squared. Okay, so I write sigma squared by delta F, and I keep on varying F naught. So this is F naught. So what should I observe? I'll observe something which is what? Constant, varies with frequency. It's flat, right? It's flat. So this is the value is 4 kT. R. Okay. So note that this is, even though we are writing in terms of frequency and there is a mean squared voltage on top, it does not mean that if I observe a frequency, if I, let's say, choose any F1, if I choose any F1 and I observe that, okay, at F1, the strength of this variance looks to be equal to 4 kTr, will I be getting a signal of strength 4 kTr, sinusoid at the of strength 4 kTr at the under root 4 kTr at the output? No. We are not going to get, because this is statistical distribution. This is not deterministic, right? What this is saying is that you observe the signal now, you are going to get some wiggling, obviously. You observe that wiggling now, you observe the wiggling again, you observe the wiggling for infinite time, and you again take a variance, you are going to get 4 kTr. That's all it says. Okay. Okay, fine. Any questions so far? Okay. So now that we have a framework to deal with noise, so obviously now you should be able to appreciate how this can be a problematic scenario in RF systems, right? To understand that, let's take an example. So let's say I have a resistor R, and in RF systems, you have seen we have band pass filters, low pass filters, and so on, right? So let's take any low pass filter, generic low pass filter. And again, let's assume that's an ideal low pass filter of certain bandwidth, BW. No amplification, amplification factor of 1. And we observe this voltage, right? So no source anywhere. I'm not expecting any signal, right? But I'll be getting noise, right? So what will be the so the noise spectral density is essentially this, right? So in this case, if I say this is bandwidth, so this will be VW. So what will I get? What will be the spectral density, observed spectral density at the output? What will it look like? Yeah, it will be 4 kTr till bandwidth, and then it will go to 0, right? So this is, by the way, this is called, let me start using the notations that are commonly used. This is power spectral density has a typically, so this is power spectral density. It has a notation of S. And if we are talking about voltage, we call it SV, right? So if I call it SV, so the power spectral density of the output, right? So there's V out, this is V out, will look like 4 kTr till certain bandwidth, till this bandwidth of the filter. Okay. Now tell me, if the filter, instead of having a gain of 1, had a gain of A, what would the power spectral density look like of the output? 4 kTr A square. Why A square? Why not A? Because while trying to figure out, essentially we are trying to figure out the mean squared voltage, right? So there is a squaring that has happened inherently. So which means that this will be 4 kTr times A square, right? So if A is more than 1, you are going to get 4 kTr times A square. Fine. So this is the power spectral density. Now, if the next question is, if I want to capture the total power that is that I'm observing at the output, whereas power spectral density is the power within that delta F bandwidth, right? Or rather, power spectral density, in principle, power spectral density, if you think about it, is the power within 1 Hertz bandwidth, right? Variance over delta F is a power spectral density. If in truest sense, the power spectral density is essentially differential of whatever you are getting with respect to, basically the differential of the power with respect to frequency. But if I simplify it, I can simply say that instead of taking this delta F to be any arbitrary delta F, if I take delta F to be 1 Hz and I observe whatever the power that comes out of the band pass filter, that power number effectively is a power spectral density, right? So if I have to observe it over, now if I say that what is the combined power over bandwidth BW, what will be the total observed power? In this case, it will be 4 kTr times bandwidth, right? Because it's flat. I don't have to integrate. If it has a profile, I have to integrate. So the total observed noise power mean squared voltage or the noise power sigma squared, essentially. All of these are same thing. These are different nomenclatures we will keep using. So we are also going to stick to that. So it becomes 4 kTr A squared times BW. Okay. Fine. So now, do you readily see an issue with this in terms of if you have to make a wideband receiver? When I say wideband, I essentially mean that you have to, this BW is higher with respect to something, right? So narrow band is BW is low, wideband is bandwidth is high. Right? Assume that you have a, if I take corner cases, I say that audio bandwidth is 10 kilohertz, let's say, or 20 kilohertz. Video, the bandwidth is 20 megahertz. So basically 1,000 times higher than the other. What can you comment on the effect of in the presence of noise? Noise will be higher, right? Because this, you cannot get rid of thermal noise. It's there. Moment you have a resistor, you have a thermal noise. Okay. And just like you saw that this antenna, we can also, when we are receiving something through the antenna, it is also kind of a resistor, right? So it's a 50 ohm resistor. So this 50, if you observe the noise through the 50 ohm resistor and it's flat, and your interest signal of interest is within certain bandwidth, and if the bandwidth is very large, you are automatically going to invite more noise power. There's nothing that you can do about it. And that noise power falls in your signal band. It's not as if you can filter it out also. Okay, so you have to live with it. The only way you can distinguish your signal from the noise is what? What can you talk about? What is the only way you can distinguish? You cannot do anything at the receiver. You have to do something at the transmitter side. What can you do? Yeah, your signal power has to be sufficiently large enough. Right? So it's like if you turn on the fan here, you'll not be able to hear me properly. I have to shout louder. Right? So it's equivalent to that. If you cannot distinguish it anyhow, you ask the source to blast more power. Okay. Okay. So that is one of the reasons. In principle, you can always use an amplifier of infinite dB, right, to amplify anything and should be able to observe. If somebody talks at the other end of this world, in principle, I should be able to put an amplifier and hear it sitting in this class also. But you cannot because there is noise, right? So, and the noise in the channel will be suppressing the signal. And if you amplify, you are going to amplify in both noise and the signal. As long as the signal that is reaching you is higher than that of a noise, you cannot do anything. Okay, you can do amplification and all those things inside the chip and hope that you are not adding more noise. But if the noise comes through in the same channel, you cannot do anything. That's the fact of life. Okay. Yes.
I assume we are talking regarding the signal to noise ratio.
Right now, we are going in that direction. Yes.
Okay. So, What are the consequences of the total noise power? I mean, with the example of the signal to noise ratio or noise power, we are talking about one particular frequency. We are not bothered about the bandwidth of the filter and all.
No. In that case, we are actually now. So if we are bothered about one particular frequency, why should I actually open the channel for the entire band? Right? If I'm bothered about one small narrow band, one frequency, I will have filter around only that frequency. I need not open up the entire band. Let me contextualize what he is saying. So this question is, let's say I am observing one sinusoid, which is a signal, right? And so, and I have this filter, which is of bandwidth BW. I'm observing a noise power of this value, right? But if the signal is also at only a single frequency, then why do I bother if the noise is spread across and the signal is at a single frequency? Is that what you are saying? So the question is valid only if I am interested in one single frequency. And if I am interested in only one single frequency, I will not have this window of filter which is so wide. I will have a bandpass filter around that frequency. The reason, so essentially, now the question boils down to characterizing your design. Let's say you have designed something, you have designed a receiver, right? Then you have to characterize in a certain way to figure out whether your receiver is noise resistant or not. So how will you characterize your receiver? One way to characterize the receiver is to say that, obviously, I'll apply a tone, that is a sinusoidal frequency at anywhere within the bandwidth, and I'm going to observe whether strength that is received and so on. And I'm also going to observe what is the noise that I receive, right? And an additional set of measurements, essentially. I have to see the signal strength that I'm receiving. I have to observe the noise that I am receiving. But the noise is coming from the entire channel. But if you absorb, if you apply only one tone, the tone is only coming from only a part of the channel, right? So another question is, how do I characterize? I can say that I will apply tone at all frequencies and find out how much the tone is higher than the noise. Alternatively, I can simply say that, okay, I understand this has a profile, and I'll just assume that the profile makes sense, right? So, and in this particular case, if it's a flat profile, I can apply a tone at any one point in the channel, right? I can apply a tone at only one point of the channel. I can extrapolate to say that it will be the same everywhere in the channel. Okay, and then only by characterizing the strength of the tone with respect to the entire noise, I am good, right? Yes.
Like we have considered the example of band pass filter and low pass filter.
Yeah.
So we are assuming that signal from the band pass is coming to the low pass. That is why we have taken into cases.
No. So that's not what I meant. So what I essentially meant is that, so if you have this sliding window of bandpass filter and you slide it all the way to ZC, then you essentially get a low pass filter, right? So that's all we're doing. Oh, fine. So now this is as far as the noise from a resistor is concerned. Okay, but there are we are not limited with the noise from a resistor only. As it turns out, any element, any dissipative element, I'm not proving this again, but as it turns out, any element that dissipates power is noisy. Okay, which essentially means that capacitor is not noisy, inductor is not noisy, but resistor is. Similarly, transistor is, right? Transistor also dissipates power, right? So it's noisy. So if I talk about a MOS transistor, so the noise in the MOS transistor is characterized in two ways. The same thing that is, I mean, it can be characterized in two ways. I'll show one of them and the other I'll show later. So let me not introduce the noise right now. So let's say you have biased it with ideal voltage sources, and you observe the current, right? This IDS will be whatever. If it's in saturation, mu n C ox W by L VGS minus VT whole squared by 2, and so on. But on top of that, you are going to get some wiggling, right? So that wiggling comes because, again, you have a channel charge. You have a channel, you have a charge in the channel, the charge wiggles, density of the charge changes ever so slightly. So whatever crosses the barrier, whatever crosses on the, over to the drain junction is different from whatever you expected. So which means, again, you have wiggling, and that wiggling is essentially modeled as an additional current source between the drain and the source, right? So this again is called IN, and the path spectral density of this IN is 4kT gamma times GM, right? Where, so it's essentially 4kT gamma times GD naught, where GD naught is equal to GM in saturation. Okay. And this gamma is a fitting factor, and that for long channel devices comes out to be 2/3. For short channel devices, it's slightly more than 2/3, but we'll go with 2/3 because we're not bothered about the small differences. As long as we are in the ballpark range with the hand calculation, we are good. Okay. Now, as it turns out, in a MOSFET, if you have done in 610, did you do layout? No, right? So, but I should be able to appreciate this anyhow because you know the cross section of a MOSFET. So, if you think about a cross section of a MOSFET, so this guy is the oxide, and this is the metal gate. Right? But in polysilicon, in CMOS, you hardly ever use metal gate. You use polysilicon. In most cases, you use polysilicon. But that's the reason it is important is polysilicon has higher resistivity than metal. Okay. But let's assume we are not bothered with that. We need a number. So let's say it is some material which has non-zero resistivity. Okay. So now, why is this important? It's important because when you connect the gate to anything, right? So you'll not be able to connect the gate distributedly all throughout on top of the gate. You are going to make a contact, right? So you are going to kind of from the top, you are going to drill a hole. On top of the chip, you are going to drill a hole that lands on the top of the gate or at the side of the gate. As it turns out, you never land anything on the top of the gate, you land it on the side of the gate. Otherwise, you stand to disturb the channel underneath the gate. So typically, the drill is somewhere here. So you drill it here and you make a contact here. Okay. So the why it is important because now the signal is coming all the way from here. But now you can think of it like this is a capacitor where the signal is coming on one side of the capacitor plate, but it has to also reach to the other side of the plate, right? So this guy has to reach on the other side. It's not a problem if the resistivity is 0, it's instantaneous. But the resistivity is never 0. It will have some finite value. And on top of that, you can assume that this is a distributed channel because underneath this, you are going to have a capacitor here, capacitor there, and so on. It's a transmission line essentially. Right? You have resistance. Instead of inductance, you have distributed resistances, and within these resistances, you have capacitances connecting to the channel underneath. Right? So naturally, it will take some time for the signal to go from one end to the other. Right? So in this discussion, that the time that it takes to go is not of a concern. The part that is of concern is there is a resistance associated with it. Right? So when moment you have a resistance associated with it, you have a problem, because now you essentially have a resistance which goes to the gate. And does this. Okay. So I call this, let's say, RG. And I had this IN. So assuming the transistor is in saturation and neglecting channel length modulation and all, I intend to find out what is the noise current. By the way, noise is always a small signal current, because we are not expecting wiggling which is higher than that of your signal. I mean, then anyway, your design is useless. If it is there, you have to somehow make it smaller. The moment you make it smaller, you can use all the small signal approximation. So when you do small signal approximation, you can replace the transistor with a small signal equivalent and do all your analysis about noise. So that's a good thing about noise analysis, all small signal. So if I have to find out what is the incremental small signal current here, right? So let me call this IDN. And I want to find out IN, total IN, both because of RG and because of IDN. How should I go about doing it? Assuming that this is a small signal approximation. So before that, I didn't show you how to model the resistance of the noise of the resistor. I showed you how to model the noise of the transistor, but it's a mistake on my part. I didn't show you how to model the noise of the resistor. So let me do that before I come to finding out the current. So what did we say? We said that you have a resistor, and if you observe this voltage, you get some, it is equivalent to saying that I have a, if I put a band pass filter and I observe the voltage, so V naught squared, again, let me be consistent. I basically say that SVR is essentially 4 kT, right? So I want to model this, right? I want to model this as a voltage source which has all the power corresponding to this noise spectral density encapsulated inside it, and assume that the resistor is noiseless, because noiseless resistor is easy to handle, at least in calculation, right? What I'm saying is this noisy resistor should be equivalent to this, where I have a Vn which is noisy, but this resistor R is noiseless. So if I want to do that, what should be the power spectral density of Vn? Pardon? Power spectral density is independent of bandwidth. So if we have to find out the equivalent of these two models, what experiment are you going to do? You're going to again put a band pass filter, observe the power and the output of the band pass filter at 1 Hz bandwidth, and both of them have to be equivalent. Then only these two models are equivalent. So if they are equivalent, what should be the power spectral density of this voltage source? It should be 4 kTR, right? So basically I say that SVN has to be equal to 4 kTR, and R is noiseless, right? Just like in case of a transistor, I just readily showed you the model where in this case, this transistor is noiseless, but the noise sources have been pulled out of the devices, right? The noise, in principle, you can never pull out a noise source, right? But this is a model, it's a mathematical model to help us think about. Okay, fine. So now what is our new model, new overall model? So this RG, this RG is noisy now. I want to make it noiseless and replace it with a noise equivalent voltage source, noisy voltage source plus RG. So what should I do? Right. So basically, whatever I find is R. So wherever I find this R, I have to replace it with this contraption now. Right? A voltage source in series with R. Right? So I replace this with a voltage source, Vn, in series with Rg, where now Rg is noiseless. Okay. So now I want to find out the observed noise, total observed noise, In, flowing out of the drain. Now, can you comment on, okay, I already told you we can do small signal analysis, right? So do I need those extra voltage sources that I have? Small signal I don't need, so I'll just basically get rid of them. In the incremental model, they are all shorted. The transistors also, I can replace it with the incremental equivalent. So I'm not replacing it because incremental equivalent is bigger to draw than a transistor. So I'll keep it as a transistor. But I'm doing an incremental analysis, right? So what is the next step? How should I find out In? Superposition, right? Because again, linear, LTI, right? Linearity is sufficient for superposition. We'll just do superposition, right? So what will be In here? In will be equal to, so I take one source at a time. Let's say I take IDN and not take Vn. So Vn is essentially shorted, right? So what will IDN do? So IDN will simply go in this route, right? Will it go through the transistor? Because gate and source is shorted, so it will not go through the transistor, it will go bypass. So In will be equal to IDN. And then, but this is only because of IDN, right? But then I have noise due to Vn, current excitation due to Vn. What will that excitation be? Plus Gm times Vn. Now, note that I have not paid attention to whether it will be plus or minus. Is that relevant? Before that also, in principle, why is it not relevant? Mathematically, I'll do squaring, but in principle, why is it not relevant? Because firstly, I don't even know, right, whether it's going in the one direction or the other. It's noise, and they are kind of uncorrelated, right? The noise in the, again, I introduced a term, uncorrelated. So when I say uncorrelated, what does it, something comes in your mind. What does it come in your mind? Then one is not dependent on the other, right? Whatever happens here doesn't influence the other and vice versa, right? So in principle, even though this is happening, at 0th order, I can say that this is uncorrelated, but in principle, it's not, because if something happens at the channel, at the gate, obviously it is going to affect the channel also, right? But for all practical purposes, I can still keep it as uncorrelated. So I need not bother about the sign of whether I am doing plus or minus. Right? This sign, you can as well keep plus, as well keep minus, because they are not going to cancel each other with respect to time. Right? Fine. So now when I wrote this, it is assumed that I am doing with respect to time, right? Because I observed it now, maybe I found something, I observed it next time, I found something. So I'm going to get all these things with respect to time, ensemble of observations with respect to time. So then what? But I know that noise with respect to time doesn't make any sense. So what do I need to do? I need to find the mean squared value, right? So if I have to find the mean squared value, what do I need to do? I basically have to simply firstly square it, right? So n squared, if I do, I am going to get IDN squared plus GM squared Vn squared, plus I'm going to get another term, right? The expectation of, again, I mean, I'm skipping multiple steps because this will come to 0. IDN times GMVN. Right? When you do, I mean, first, any statistical parameter, how do you find out variance? You do a correlation, right? And then square it. So you get this cross terms between multiple terms. And this guy is going to go to 0, right? Because they are uncorrelated. So this guy is going to go to 0. So essentially get squared of the individual terms, right? So that eases our life for whenever you're finding any noise due to uncorrelated events, you write out the expressions and only square the individual terms, right? And that eases our life. So essentially, your SVN is essentially S, or in this case I, right? SIN is equal to the sparse spectral density because of your noise current in the transistor, which is 4 kT gamma GM plus GM squared times 4 kT RG. Okay. So that's how you find out the total current noise at the output. But obviously you are not interested in the noise, you are interested in the signal. And if it's a common source amplifier, your signal is also applied at the gate, right? So let's say I apply the signal at the gate. Yes.
While calculating the noise, why aren't you worried about the gate capacitance?
Yes, I have not taken any capacitance till now. Obviously, if there is a capacitance, it is going to shape the power spectral density, right? So in that case, we have to take that into account. We'll come to that.
Like placing VN and RG the other way, that will not shape.
I didn't understand.
VN at the gate and RG before that.
No, these two come together, right? You cannot.
RG left and VN right.
Okay, good question. Should it? I mean, no, let me ask you this then. So again, this is slight digression, but I would have come to it anyhow. So let's talk about this. So his question is, so you have a capacitor here, right? You have a CGS capacitor here, right? So I just put this capacitor here. And this is VGS. And I do this VN. Because ultimately this is a model, right? This is a model. I can put the noise source on the left or the right, it shouldn't matter. And I observe VGS. Will both VGS be same?
One is like the low pass filter, another is.
I am observing the voltage across the capacitor. No, you don't have to do any approximation. My question is, in this case, the observed VGS, consider deterministic VN. Let's say VN is a sinusoidal source. Will the voltage across the capacitor be same in both cases? Will the current in the loop be same in both cases? Yes, right? So, and then if the current is the same, the voltage across the capacitor will also be the same in both cases. But I didn't understand what is the issue.
So I was thinking that is a kind of low pass filter. It will filter out all the higher frequency stuff from VN and will just apply directly.
In both cases, it is low pass filter, right? If you observe, I mean, whether it's a low pass or high pass depends upon where you are observing. also, right? My observation is point is not changing. It is still across the capacitor. Right? Right? Okay, fine. So what's the time? We still have about 5-6 minutes. Okay, fine, we can do this. So we have a voltage source, which is deterministic. This is wanted voltage source. I'm not showing any biasing. I'm also not showing any current, so noise current now, because just like, all noise current and the intended signal appear at the same time, but I can do superposition. So when I'm doing signal analysis, I'm not taking into noise into account, right? So this is signal analysis now. This is VI. So what will be the signal current? GMVI. So what is the power contained in this? Again, when I say power contained in this, don't look for resistor, simply square it. I'm talking about mean squared, right? So I squared sig is essentially equal to GM squared VI squared, right? Again, if it is a sinusoid, you have to do VP squared by 2 and all those things, but let's keep it at that. So essentially the part that we are looking for is essentially the signal to noise ratio, right? Not only signal, not only noise. Okay. So what we are looking for is signal to noise ratio, where the signal power is GM squared VI squared, right? And if this is a sinusoid, right? If this is a sinusoid, then I'll have to find out the total power by finding out integral, all those things. If I am looking for the entire band, the power contained in the entire band for the signal, I have to then multiply with the bandwidth, right? So the same thing I have to do for the noise, right? So I'm doing some ratio on the top, some ratio on the bottom. If the bandwidth is the same for both cases, I don't have to bother about the bandwidth, right? I'll just do this GM squared VI squared divided by whatever I got for the total noise, right? So that is 4 kT gamma GM plus GM square 4 kT RG, right? 4 kT gamma GM plus GM square 4 kT RG. Okay. Yeah, what you are saying is correct. So I should be more careful here. If this is a sinusoid, then GM squared VI squared becomes the total power, right? So, but let's say the power spectral density of the input, let's say this, let me refer to as SV in, right? So in that case, it should be GM squared times SV in, right? All good. So this is a better way of doing it, right? So thank you. So I should say SV in.
Yeah, just you should put S, like the power spectral density of the current.
I didn't understand.
Instead like your I square, instead of that, you should put the power spectral density of the current.
Power spectral density of the current itself is GM squared times SV in, right? Oh, okay, correct. Yeah, yes. So it should be SI sig, right? Yeah, thank you. So essentially your SNR becomes this. Now, as it turns out, we can make another, in most low frequency applications, in most analog applications, as it turns out, this RG you can kind of neglect. Right. So the reason is not very evident at this will not be evident to you at this moment, but the level of so let me put it this way. What is the source of RG? The source of RG is the routing of the polysilicon on top of the on top of your transistor, right? So would you expect that routing to be really large or really small? It is in your control. You would want it to be very small, right? So which means that if you do not want a transistor to have a very long routing in terms of W, right? So for example, if I'm not looking at from the top, right? I'm not doing a cross section, I'm looking from the top. If I look from the top, then let's say this is your, so this is the drain, this is the source, this is the gate. Okay, I'm looking from the top. So you have a contact here. So all this entire, so this essentially this is a W, right? If you have a very large W, then you have a very large RG, right? So what we tend to do normally is to say that, okay, I understand this is a problem. So we'll not have a very large W. We're going to split it into two small Ws, right? So I'll do two small Ws, maybe two different transistors, let's say, of, okay, this looks the same, but W by 2. This is drain, this is source. This is source, this is drain, let's say. Well, yeah. And I connect this in parallel with some sort of metal, right? With a much lower resistivity metal. So in principle, I can say that as far as the signal is concerned, it is still seeing a transistor of width W. Because if I connect them in parallel, obviously, otherwise we will not see. Let's say I connect these two in parallel. Right. So then effectively, the signal still sees a transistor of width W. Nothing changes as far as signal is concerned. But can you comment on RG? And how, I mean, if the scaling is linear, how much will it be less by? It will be less by half in each of these two transistors. And they are in parallel. So it will go down by a factor of 4. Right. So you can do all sorts of this type of layout techniques, right? Or splitting the transistors into multiple multiple sections and put them in parallel to reduce RG. So to some extent, RG is in your control. Right. So between these two terms in the denominator, the first term is the dominant one, because the first term is hardly ever in your control. Because GM you are going to require, because your signal requires some strength. So moment you select a GM, nothing else is in your control. KT is not in your control, gamma is large X is not in your control. Right. So the dominant term for noise in the denominator is the 4KT gamma GM. Right. If that is the case, bear with me for a minute. So your SNR is approximately equal to GM times SV in by 4KT gamma. Right. So the reason I wanted to show this here is because it seems like if I only concentrate on the noise term, it seems like increasing GM increases noise. But we are not interested in only noise. We're also interested in signal. In fact, we're interested more in signal than noise. We're interested in signal to noise ratio. But signal to noise ratio looks like it improves by increasing GM. Right? In principle, why? Because the sparse spectral density of the noise is proportional to GM, but the sparse spectral density of the signal is proportional to the square of the GM. Right? I'm interested in the power of the signal. Power of the signal means that you are squaring with respect to GM, right? But thankfully, the noise is proportional to GM. Noise power is proportional to GM. So the noise power increases at a lower rate with respect to GM than the signal power. So the ratio is always in our favor. So that is why if you have to make good, very low noise design, you have to size it for a large GM. And when you size it for a large GM, you end up burning more power. Right? So that is why low noise designs almost invariably burn more power. Okay. Okay, fine. We'll stop here. We'll see in the next class. So today, I think we'll have meet with few of the students, right, Samir, in the second half. You have sent out the fine. Oh, sure. We'll do it after. Today, not many people are there. So I'll send out the answer sheets and then we'll distribute. Huh? In my office.